Hello, class. This is Mr. Hart. In this podcast, we want to finish up the motion and force chapter of our textbook. And specifically, we want to talk a lot about gravity. Now, you are probably familiar with what gravity is, but we want to kind of describe it more quantitatively in physics terms. Okay, but before we can do that, we need to clarify a couple of things. Okay, the first thing is the difference between mass versus weight. Okay, so let's say you get on the bathroom scale in the morning and you measure your weight, right? When you are measuring how many pounds you weigh, you are determining your weight. Okay, so a scale determines the weight of an object. So what is the mass? How do we distinguish between these two? Sometimes we say them and we use them interchangeably, but they have a very distinct meaning. So let's look at the difference. Okay, so the mass is the amount of material in an object, whereas the weight is the amount of gravitational force of an object. Okay, so let's just say I have a random object over here. Okay, the mass is literally describing the number of atoms in this object. Okay, if I took all the atoms in this object, okay, and I looked at how many there were, okay, the mass would describe in some way how much material I have. Okay, it's usually measured in kilograms. Okay, but it's describing the amount of material in that object. Okay, whereas the weight is describing not only how much material I have, but how much that material pulls down on the earth or pulls down towards the earth. Okay, the gravitational force of that object. Okay, so you will always have the same mass no matter where you are. Okay, this object would have the same mass on Earth, the same mass on the moon, the same mass in the middle of space. Okay, but the weight is going to change because the gravitational pull is going to change. Okay, it will weigh more on Earth than it does on the moon. It will weigh more on Earth than it does in space, right? So its weight can change because its gravitational pull can change. But the mass never changes, okay? The amount of material is always going to stay the same, okay? So mass is the amount of material. The weight is how much that material gets pulled down by gravity, okay? Then in class, we did an activity about supporting loads and structures, okay, with weight, okay? And then we start to look at gravitational acceleration, okay? So Galileo and some other physicists were able to determine how quickly the Earth pulls things down, okay? For every object, this acceleration is the same, okay? There's the legend that Galileo went to the top of the Tower of Pisa and he dropped two objects off the tower and they hit at the same time, okay? We don't know if that story is necessarily true, but the principle still is, okay? He was able to determine that every object fell at 9.8 meters per second, okay? And if you remember when we talked about acceleration, meters per second squared is the same as meters per second, okay? So every second, this object will be going 9.8 meters faster than it was before, or 9.8 meters per second faster than it was before, okay? So it's going to be falling really slowly to start with, but it's going to get speed the longer it's been dropping, okay? So we assign this little g, okay, and this is constant no matter where you are on the Earth or on the surface of the Earth, okay? So we can use this in an equation, okay? So the velocity of an object is just going to be equal to the gravitational acceleration times how long it's been falling, okay? So in order to figure out how fast something's going to be falling, we just need to know how long it's falling and then times it by that gravitational acceleration, okay? Let's try an example problem really quick. So if an object has been falling for 2 seconds, okay, how fast is it moving? So we know that g, the gravitational acceleration, is constant. It's equal to 9.8 meters per second per second. 9.8 meters per second, or second squared. Okay. We also know that it's been falling for 2 seconds. Okay, so t equals 2 seconds. And then to find the velocity, we just times them together because v equals gt. We just take g, which is 9.8, and we times it by 2, and we get 19.6 meters per second, okay? So after an object has been falling for 2 seconds, it is moving at 19.6 meters per second, okay? That's pretty fast. So every second you're moving 19.6 meters, okay, or about 60 feet. Okay, that's pretty crazy how fast that's pulling you down. Okay, so that's how fast you're moving. Not how far you have gone, but how fast you're moving. Okay. So using this simple equation, we can figure out how fast any object will be falling, okay, after 2 seconds. Okay? So does that mean that all objects fall at the same rate? Okay? According to Galileo, it means that it does, okay? But there's a problem, okay? We don't live in a perfect world, and you probably understand this principle. If you drop a piece of paper or a feather, okay, something that's nice and flat and light, and you drop it, and then you drop a hammer, for example, okay, which is nice and heavy, okay, you'll know that the hammer is going to hit the ground first, okay? Well, according to Galileo, they should hit the same time. So what's the problem here, okay? The problem is we don't live in a perfect world and we have air resistance, okay? So what is air resistance, okay? It's the resistance of movement from the air itself, okay? That air is going to put a force on objects, okay, that are falling. It's going to put force based on the volume. So you can imagine as this person spread out, okay, the air is going to be pushing up on them, okay, all along their body, okay, trying to resist their movement. Okay, they don't want them to fall through the air, just like the water. When you jump in water, it doesn't want you to move through it, okay? It's going to have some resistance. So heavy objects like people and hammers push through just fine, but light objects like feathers do not, okay? And so they will fall slower because they have a lot of resistance, okay? If we were in a perfect world where there was no air resistance or friction, everything would fall at the same rate, okay? Like Galileo said, but we do have this air resistance, okay? The more massive an object is, the easier it will cut through the air and have less resistance, okay? The lighter it is, the more air resistance you'll see, okay? Other things that affect it are the volume. The bigger in size an object is, the more air resistance it's going to have, okay? This is why the skydiver, you'll notice they spread their arms like this. This is to give them more volume, so that they have more air resistance to slow them down. What happens when they bring their arms in, though? If you've ever seen them, they'll start to move faster because they have less volume. Okay, they'll cut through more. Okay, so things that affect the air resistance are the mass. Okay, more mass, the less you feel the air resistance, and the volume. Okay, the more volume you have, the more air resistance you're going to have. Okay. So if you want something to cut through the air, you want it to be very massive but very small. If you want something to have a lot of air resistance, you want it to be very light and very large. Okay? So hopefully that makes sense. In class, we did a lab that describes this, the gravity versus air resistance. We explored some of the different objects and how air resistance affected them. Okay? And the last thing we want to talk about is gravity and distance. Okay, so a lot of these ideas are when we're talking about the surface of the earth. We're very close to the surface of the earth. Okay, but let's talk about when you're at a very large distance away from the earth. Okay, so anything that's within a good 10,000 meters of the earth's surface, okay, isn't going to see any difference, okay, in the amount of gravitational pull. Okay, if you're in this range of the Earth's surface, okay, you're pretty close. Even like satellites, for example, you're not going to see a huge difference in the gravitational pull. It's pretty much going to be the same. You're still going to have that acceleration of 9.8. Okay, when you get further and further out, though, okay, let's say you double the distance. So if this is the center of the Earth, here's the surface, and then you are twice as far out from the surface, okay, that's when you start to see a decrease in gravitational pull. So instead of accelerating at 9.8, you would accelerate around 2 meters per second squared. Okay, and so we have a rule that describes how much gravitational pull you'll see, and it's called the inverse square law. Okay, and you'll hear this word a lot as you go into higher physics and science classes. Okay, the inverse square law just says that if you double the distance, okay, that you are out from an object, okay, or from the Earth or whatever it is, whatever gravitational body, if you double the distance, you'll see a fourth of the force. Okay, so if I'm twice as far out, I will see 1/4 the force I would see right here. Okay, if I was 3 times as far out, I'd see 1/9 of the force I would see. Okay, so it's written like this: 1 over r squared, or the distance squared. Let's actually do d. So 1 over d squared. Okay, so if I double the distance, for example, that's 1 over 2 squared, which equals 1/4. Okay, so I double the distance, I get 1/4 of the force. Okay, if I 1/3 the distance, or I say triple the distance out, I get 1/3 squared, which is 1/9 of the force. Okay, if I do 4 times the distance, it's 1/16, and so on. Okay, so we call this the inverse square law. The further and further you go out, the square of the distance is how much less force you have. Okay, so again, it doesn't affect us because we're pretty close to the surface. We don't change our distance very much. Even satellites are pretty close. Okay, it's when you really start to get far out away from the surface that you start to see these different gravitational pulls. Okay, so it's not constant. It is for us on the surface, but the further you go out, you start to see less and less force. Okay, all right, so that's all for this lesson. Hopefully that all makes sense. Let me know if you have any questions, and thank you for watching.